Picture this. You're on the way up the stairs at school after a long class, looking at your phone, and you bump into your friend who's doing the same. You both drop your books, but it turns out they're identical. Whose book is whose? Of course, you could just look inside of them, but what if that wasn't possible? Instead of books, consider two identical balls rolling quickly towards each other. From far away, you're not quite sure whether or not they'll collide. If you blink right as they're about to come together, you might miss their interaction entirely. Then you'd have no idea about the final position of each ball individually, and just that one is here and the other is there. In reality, this is what happens to all atoms, electrons, and neutrons. This phenomena is called indistinguishability, and is the reason why computers exist, neutron stars are stable, and why we're alive as it is. But who cares, you might wonder. Identical particles are indistinguishable, but why does that matter to us? And you'd have a good point. It doesn't matter to us which is which, but it does matter to the particles. Different types of particles react to this indistinguishability in different ways. It turns out that all known particles in the universe can be broken down into two categories. Bosons, named after Indian physicist Satyendra Bose, and fermions, named after Italian physicist Enrico Fermi. We break particles into these different classifications based on the quantum mechanical spin, a fundamental characteristic of particles like their charge or their mass. Some classic examples are photons and the recently discovered Higgs boson, while fermions are particles that you might be a little bit more familiar with. Electrons, protons, and neutrons, the basic constituents of atoms, are actually all fermions, so more or less you're entirely made up of them. Bosons are actually happy sharing the same quantum mechanical state, meaning that the position and their alignment of their spin can be the same, but quantum mechanics actually forbids fermions from doing that. This gets really interesting though when you realize that atoms are not actually hard spheres, but they act more like fuzzy balls. In quantum mechanics, we don't have a way of describing where a particle actually is. All we can do is describe its probability of being in a certain place, and this is called their probability distribution. Particles actually interact with each other through their fuzzy probability distributions, and this is what provides the really cool differences between the two classes. In order to see the difference in these interactions, we have to go to low temperatures compared to the energy of the particles. Often this is called the quantum limit. At these low temperatures, the particles get closer together and their fuzzy probabilities start to overlap. While bosons are quite happy to snuggle up close together, fermions hate overlapping like this and start to push each other apart. This force creates extra outward pressure in the system, often known as degeneracy pressure. This might all sound really out there, but we can actually see all of this phenomena on the most massive scales. Let me give you an example, but first, I need to teach you a little thing about stars. Now, stars remain stable through a combination of forces trying to pull it together and push it apart. First, gravity from the star's mass tries to pull everything into its center, but this force is counteracted by radiation pressure from nuclear reactions in the star's core. These reactions require fuel though, and when all this fuel is used up, gravity will begin to win this tug of war. So what happens? Well, something else starts to fight back. As the hot plasma in the star gets pulled together, the fuzzy fermion balls will start to overlap with each other and push each other apart. In what's called a white dwarf star, electrons push back hard enough to counteract gravity. But in what's creatively called a neutron star, the neutrons from the parent star also need to get involved. These stars are very dense. A sugar cube-sized piece of a neutron star would weigh just about as much as a mountain. Humans have measured both of these types of stars. White dwarfs are fairly common, with the brightest star in the night sky, Sirius, actually being a binary pair of stars including a white dwarf. Neutron stars are a bit more rare, but we've also seen them, including the gravitational waves that a merging pair of them produces. Now back to those bosons. What happens to them in the quantum limit? Well, unlike fermions, bosons don't actually mind having their probability distributions overlap. In fact, they actually enjoy it, and so they tend to clump together in their low energy states. This forms a state of matter called the Bose-Einstein condensate, where all of these atoms act as if they're a single atom, and even for amounts that we can see with our own eyes. We can see a Bose-Einstein condensate made up of helium at extremely low temperatures in this video. Notice how initially at higher temperatures, the helium is very turbulent as it boils and evaporates, even at these low temperatures. But as it reaches about 2 Kelvin, it exhibits some weird properties. First, it settles down and becomes completely still, and it even starts to leak through the ceramic bottom of this beaker. This helium has formed a superfluidic Bose-Einstein condensate with some even weirder properties that researchers are currently working on. It is weird to think that there is such a difference between these two types of matter, but that without it, life would not be possible as it is. So I'll make sure to thank Fermi and Bose before bed tonight. Thanks for watching.